Hi, welcome to the 8th session on group theory. As I promised in the last lecture, this will be on dihedral groups. For each natural number n greater than or equal to 3, there is a dihedral group denoted by d suffix n, which is of order 2n. But today, to make things very crystal clear and concrete, we will focus only on n equal to 4. Therefore, we will be dealing with d4, which is a dihedral group of order 8. That will be non-abelian groups. And usually, this is not dihedral groups are not done in the first course in algebra. Most often, even at MSc level, many teachers don't do it. That's because dihedral groups arise as the group of symmetries of a regular n polygon. Okay, polygon of n sides. What are they? They are just in the complex plane. In the unit circle, you mark our nth roots of unity and create a polygon out of that. That will be regular n polygon. So you want to know what are the symmetries. Okay, don't worry about it. At least when n equal to 4, I'm going to explain. N equal to 3 and 5, I will quickly do it at the end. Okay, do it. And one more thing, this is a fantastic thing because even algebra is what they do is later they will do what we are going to do at the end. That is, with very few symbols, okay, they will have only two group elements. We will call them an R and S. Then they will say R to the power 4 or R to the power n equal to identity and S squared equal to identity and R, S, R equal to S. With these relations, we can fill in the Cayley table. What is the Cayley table? Suppose the finite group has n elements, write them G1, G2, Gn. Of course, G1 will be identity. Similarly, G1, G2, Gn as a column type. Okay, then I have to multiply Gi times Gj equal to what? You will see I can fill in all this with these three. That is R squared equal to, sorry, R to the power n equal to identity, S squared equal to identity, R equal to S with this. Okay, you will really learn abstract algebra, it is best. In fact, algebras usually prefer this definition because they don't have to worry about the geometry, they can work with that. But knowing the geometry helps us, later we will see in the course. Okay, lot of preliminary, let's get started. Okay, there is an article of mine on which is available, the name dihedral group. Yes, and I have to, yeah, I forgot to bring the pen. Yes, let me see whether I can do that. Yeah. So, what is the dihedral group? So, let's stick to n equal to 4. Okay. And this is, let us think of this as a square. Okay. This is a square. This is the origin 0, 0. Okay. These are the points. I'll denote the vertices by 1, 2, 3, 4. Usually I should have started 1 here, but you will see to save time I had already written the wrong way, so let me stick to that. Okay, so this is the square. What we want to do is the symmetry of those symmetries of the square. Okay, what does it mean? That is, we are going to do that. Okay, you see that this is, I am going to rotate the square by 90 degrees, that is pi by 2. So let us mark these things 1, 2, 3, 4 other thing. When I rotate anti-clockwise, remember this shows anti-clockwise. Okay, then this 1 comes to 2, 2 goes to 3, 3 goes to 4. Do you see this? And in terms of permutation, I will simply write this R correspond to the permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Is that clear? Now R squared, what does it mean? You rotate it by pi degrees. That is 180 degrees. Therefore, when I do this one rotation, that brings me to 2. One more rotation will bring it to 3. Therefore, 1 goes to 3, 2 goes to 4, 3 goes to 1, and 4 goes to 2. 4 goes to 1 and 1 goes to 2. You understand this? Yeah, you follow it up. That is, you follow this twice. 1, then the once more rotation by in the anti-clockwise direction by 2, therefore this 1 goes to 2 here, this 2 goes to 3 here, right? And this 3 goes to 4 and 4 goes to 1. Okay, have you understood this? Right. So 1 goes to 2 and this 2 goes to, so I'm just rotating it or anti-clockwise direction. Okay, I hope I did it correctly. Okay, right. And this 3, again the same thing. Okay, 1 goes to 2, 2 goes to 3. Okay, so you can see when I do 2 pi, that is full rotation, then I'm going to go to identity. Okay, this is our R4 equal to 5. This is the one identity. Okay, these are the groups of symmetry. This means I have a piece of paper. Let me see, I had somewhere. Yeah, see, do you see that? I have a piece of paper, okay, marked with 1, 2, 3, 4. Can you see this? Yeah, and rotate it. Okay, anti-clockwise direction. Okay, anti-clockwise direction for me is this way. So you can see what happens. Okay, and then once more 2, and once more 3, and once more 4. You will be back to whatever you had. Okay, I hope I did it correctly. Okay, right. So this is what we are doing. So you get, this is the symmetry. Then there is another symmetry which is known as reflection. This is reflection. I can take, let us assume this center of this square is origin and the sides are parallel to the axis. Therefore, I can kind of reflect the square with respect to the x-axis, right? Therefore, when I reflect, this 1 goes to 2 and 4 goes to 3 and 2 goes to 1, 3 goes to 4. You see that? So 1 goes to 2 and 2 goes to 1, and similarly. Okay. Therefore, this is a product. If I write as a permutation, you can see this is a product of two transpositions. 1 goes to 2 and 3 goes to 4. Notice that S squared is identity. Okay. For various reasons. One reason is do once more and reflect along x-axis. This 1 goes to 2 and 2 goes to 1. Therefore, 1 goes to the original place 1. So on and so forth. Or the other way around is, look at this as a permutation. This is a product of two disjoint cycles, therefore they commute. Therefore, the whole squared, S squared will be 1 2 squared and 3 4 squared. And 1 2 squared being transposition is identity. This is also 3 4 squared is identity, therefore S squared is identity. Right? Now you can see the next thing is the reflection with respect to y-axis. Right? When I reflect, then this 4 goes to 1, this 1 goes to 4. Do you understand this? This means this goes to this place and this 4 goes to come to this place. And similarly 2 and 3. Okay, you see that? Therefore, what is this? This is again product of two transpositions 1 4 and 2 3. Let me just check. I enabled recording. Yeah, okay. Right? Now I can also reflect along the diagonal 1 3. That means when I reflect, this is the mirror, therefore 1 and 3 will remain fixed. Then 4 goes to go to the place of 2 and 2 goes to the place of 4. Therefore, it's only a single transposition 2 4. Yeah. And similarly, I can reflect it along the diagonal 2 4. Okay, that means 2 and 4 will remain fixed and 1 goes to 3, 3 goes to 1. Therefore, it's a transposition 1 3. Okay, these are the 4 reflections. Sorry, 4 reflections. So what have we got? In all, I have got 8 mappings. Okay, in terms of vertices, I have 8 mappings. Okay, one is R, but R is R, R squared, R cubed, R to the power is identity. The other one is S, which is a reflection along the x-axis, and that is S squared equal to identity. And there are other 3 reflections. What are they? They are got by reflecting along the y-axis or reflecting along 2, 4 or reflecting along 1, 3. Right? The diagonals. Right? Now what we want to do is we want to find out what is RS, SR, RSR, etc. Okay. We are going to see once I know R and S, which is the reflection about the x-axis, the other reflections will follow from that. You understand what I'm saying? Okay. Remember, all these mappings are composition of mappings, right? They are the kind of mappings of the vertices. So I have to compose. So I want to see what happens to that. Okay. Let us go slow. Again, I will show the picture, and finally you will see. You can throw away the picture. Okay, if you are a pure algebraist, you can throw away the picture and try to concentrate only R and S. You will see that. Now let us see what happens to RS4. What does R do? It rotates. Okay, it rotates in the anti-clockwise direction by 90 degrees or pi by 2. Right? When it goes, this therefore this 1 comes here, and 2 goes here, and 3 goes here, and 4 goes here. Is that clear? Now I want to reflect it along the x-axis. When I reflect along the x-axis, what happens? 4 goes to 1, 1 goes to 4. You see that? And similarly, 2 goes to here, 3 comes here. You got it? Now I want to again rotate. Yeah, if I rotate, what happens? I rotate by pi by 2, again anti-clockwise direction. Therefore 1 comes to here, and 4 goes here, and 3 goes here, and 2 goes here. You got this? Right? You understood this? Therefore what I have got is R, S, R. Now what is this? This is nothing other than reflection along the x-axis. You see that? This is the reflection along the x-axis. Right? Again, this picture will be clear. Reflection on the x-axis, 1, 2, they get interchanged, 3 and 4, they get interchanged. Do you see that? Yeah. Therefore, we got RSR is nothing other than S. Have you understood? Yeah. So, oh, I forgot to share the screen. Sorry, let's go back. I'm screen sharing. Yeah. So, I want to know R, okay, 1, 2, 3, 4. This is the original configuration of the square, and rotate it by pi by 2 in the anti-clockwise direction. Then I get this picture. 1 comes here, 2 goes here, 3 goes here, 4 goes here. Did I get it? Yes. Then I reflect this along the x-axis. Then when I reflect it along the x-axis, what happens? 4 goes to 1, 1 goes to 4. Right? And similarly, 2 and 3 interchange. Is that okay? Then I rotate. When I rotate, what does it mean? 1 comes here, 4 goes here, 3 goes here, 2 comes here. This is the picture, right? So this whole thing is RSR. Now, what is RSR? RSR is nothing other than reflection along the x-axis, because if I reflect it along the x-axis, 2 goes here, 1 comes here, 3 goes here, 4 goes here. That's what it has. And in case you have difficulty, go back. This is the picture, right? Therefore, what have we got is RSR is S. Is that clear? So now we have we have 8 elements. I'll change it. 8 elements. Okay. R, yes. Okay. And there are various other things, that is R, R squared, R cubed, R power 4 equal to identity, and yes. And then there are other elements which I want to look at. Okay. I want to say these 8 elements, the other 3, there are 3 reflections, right? This is the reflection about y-axis, a reflection along the diagonal 1, 3, and the reflection along the diagonal 2, 4. I am going to say we can get everything from here. Okay. Are you following? So the formula is for this. Suppose let us look at what is RS. RS, it says, see, RS R equal to S, okay, and therefore let us multiply both in by R inverse. This is S R inverse. But I know R power 4 is identity. That is R into R cubed is identity. Therefore, R inverse is R cubed. Therefore, it is S R cubed. You understand this? Yeah? Okay. Therefore, RS is S R cubed. Is that right? Now let's try to find the thing. So I want to get, let us look at what is RS. Okay. Now R, let me quickly do 1, 2, 3, 4. Under R it goes to 1, 2, 3, 4. Under S it goes to S is reflection along the x-axis. Therefore 1, 4, 2 and 3. Right? 1, 4, 2 and 3. Let us see where I get it. 1, 4, 2 and 3. You can see it's a diagonal. It's a reflection along the diagonal. Right? That also I can see 1 and 3 remain fixed. Therefore this is nothing other than reflection along the diagonal. 1, 3. Yeah? Okay. Now let us look at R squared is. R squared is 1, 2, 3, 4. Under R it's going to be 1, 2, 3, 4. One more R, it's going to be 1, 2, 3, 4. So I got R squared. Then S is going to be reflection along this. Therefore 4 comes here, 3 comes here, 1 goes there, 2 goes there. I hope I did it correctly. R squared into S is going to be 3 and 4. Right. Okay. Yeah. Now you can see this is the reflection along the y-axis. Yeah. If I reflect along the y-axis, what happens? 4 goes here, 1 comes here, 3 goes here, 2 goes. Therefore, this is reflection along y-axis. Yeah. Now guess what is R cubed is? In case you find it little, because geometries are weak most of the time, if you find it little difficult or fast, pause the video and go back and go through them. In fact, it's strange. I also forgot PRP. Yeah, right. Pause the video, revise, do it. Okay. First, go through what are the four rotations. Okay. Identity rotation, which doesn't mean anything, or it goes via 2 pi degrees, 2 pi radians, that is 360 degrees. The basic rotation is anti-clockwise by 2. Then R squared, R cubed, R power 4 will be identity. The next one is a basic reflection, which is S. What is that? It is a reflection along the x-axis. Okay. The top side comes to the bottom side goes to the top side, kind of thing. Okay. Of this. Now there are other 3 reflections. What are they? Reflection with respect to y-axis. That is, this side goes to this side and this side goes to this side. Okay. And the third one is reflection along the 2 diagonals. So there are 4 reflections. What we are going to do is we are going to show all the other 3 reflections can be got from R or its powers into S. What is S? S is reflection along the x-axis. This is the idea. Okay. Please review. Go back. Now what you have shown is R times S is a reflection with respect to the diagonal, one of the diagonals. And R squared is, we saw it is reflection with respect to the y-axis. Then what could be R cubed as? That's the question I stopped. The answer is clear. It should be reflection with respect to the other diagonal. Which is the diagonal? We will find out. So R cubed, I will not write everything here, it will be easier. So when I applied R cubed, what do I get? 1 goes to 2, 1, and 2, it goes to 3, 3 goes to 4, therefore 1 goes to 4, right? Right? Therefore this will be 2, this will be 3, this will be 4, right? 1 goes to 2, 2 goes to 3, 3 goes to 4, right? And 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, therefore this. Okay. Now I apply S. S is reflection with respect to the x-axis. Therefore, what do I get? 3, 2, 1, and 4. Is it clear? And what is this? 2 and 4 remain fixed. Therefore, it's a reflection with respect to the diagonal 2, 4. The line segment 2, 4. Yeah. The last one, RS was diagonal with respect to 1, 3 and R squared. So, let us quickly do. S is reflection with respect to x-axis, and RS is reflection with respect to the diagonal 1, 3, and R squared is reflection with respect to y-axis, and R cubed is equal to reflection with respect to the diagonal 2, 4. You follow that? Therefore, these are the 8 elements we have. What are the elements we have? We are having R, R squared, identity, E, R squared, R cubed, and yes, RS, R squared is, and R cubed is. These are the elements of D4, right? I want to say, and the composition, because remember R and S are mappings of the vertices, right? Therefore, there is a composition. What I want to say, yeah, just let us stop for a while, pause, review, proceed. So these 8 elements produce the symmetry of the thing. What we want to show is, remember all these R, S, etc. They are all what? They are the mappings of the vertices, or the rigid motions. One usually calls it rigid motion of the square. Okay, how you take the square and rotate it, or reflect it this way, or whatever. Okay, you understand these things. Very good. Therefore, I can compose them. Composition of mappings. Okay, because they are mappings of the sphere, mappings of the square, or mappings of the vertices. Right? Whichever way you find it convenient. I usually think of it as the vertices. It will be easier. Okay, right. Now I can compose. So what do you want to say? These 8 elements remain closed under composition. That is D4 cross D4. Okay, I can compose. Take some element alpha from D4 and a beta from D4. Then I have alpha composite beta, right? That will still be in D4. Okay, so we want to say it becomes a binary operation. Next thing we want to show is, under this binary operation, it's a group. Is that clear to all? Please understand. I know it may be tough, but the best thing will be, as usual, discuss with your friends. Keep it and explain that to him, or let him explain to you. You will see, you will understand much better than, okay? You will learn much better from your friend than from me. Okay, right. Let's go. So how do I do that? That is where I'm going to make use of the basic thing. What is the basic thing? There are essentially 2 elements, R and S. Next thing is, there is one important relation. What is the relation? When I compose them, R followed by S followed by R. Remember, composition comes from this way. When I say G composite F, what does it mean? F operates first, G operates next. Here R S R, so you can say anyway, but what it means is R S R. I start from the rightmost R, let it work. After that, let it S work, let R work. Then what do I get? I get S. Okay, this is enough for us. Okay, right? And we have, what are the 8 elements? We had already listed all the 8 elements. Okay, even though we thought of them as reflections for reflection, but we saw other 3 reflections are got from the single reflection S and powers of R. Okay, so you can forget everything, only you can concentrate on the final relations. Okay, now the abstract group theory begins from here. You go through it, you will appreciate, you will understand it much better. I'll just go slowly. So suppose, so what we have the elements are something like R, R squared, identity, R cubed, and yes, RS, R squared is, and R cubed is, right? Now take any two arbitrary element, okay? Just, okay. Some let us experiment. I can write down what is known as the Cayley table. What is the Cayley table? Cayley table says, look at the elements E, R, R squared. Hey, have I done that? I do not know whether I wrote it. Okay. R squared, R cubed, and then yes, RS, R squared S, R cubed S. Okay, this is like a multiplication table. Same thing you write E, R, R squared, R cubed, RS, R squared S. No, I forgot S. Yes, R squared S, R cubed S. So you can do all these things. Right? So you keep on doing. So you can see there are 8 times 8 products. Right? So start with some arbitrary element in this column and start with an arbitrary element in this row and multiply them out. So what way I do? I do RS here. Suppose I take R squared S. Okay. Then remember these are all composition of mappings. Therefore, you should do S first, R squared next, S next, and R next. You understand this? Okay. So this is known as the Cayley table. Cayley table can be written for any finite group. Okay, call this G1 to Gn, G1 to Gn, take some Gi here, some Gj here. What is Gi dot Gj? That will be yet another Gk, right? Because it's a group, right? It's a binary operation, therefore it must be closed under the operation. Therefore, if we take a Gi here and take a Gj here, then Gj here, then it will be Gi dot Gj, but then remember it should be some Gk. Are you following? Okay. Now what we want to do is, when I do any of those things, I will get only one of the 8 elements. Is that clear? So let us do, for example, Rs into R squared S. Right? Now let's look at what is our formula. Our formula is Rs R equal to S. Right? Therefore, right, before going to, let us, okay, let us do first few observations. I claim R power k yes, R power k is also yes for all integers k in n. Of course, k greater than equal to 4, okay, it's trivial. Okay, this we do by induction. K equal to 1, okay. And what is k equal to 2? Let us do R squared, yes, R squared. This is R, yeah, r squared. Yes, r squared. So let me do that. R, yes, r into r. Can I do that? Are you following? R squared I can write r times r times r, s times r times r. I am grouping them together. But r as r is yes. But r as r is yes. Therefore I got the result. You understand that? So for k equal to 2, correct. Pause, review, proceed. Now assume result for k. So I have to prove k plus 1. R to the power k plus 1, yes. R to the power k plus 1. But this is, I can again do the same thing. R into r to the power k, yes. R to the power k, r. You see that? R to the power k plus 1, I am splitting as r into r power k. And here I am splitting as r power k into r. Now using associativity, I can group this. And this by induction is yes. And this by what we have proved is this, yes. So we have proved for all k natural number r, k, s, r power k is yes. In particular, r power k s is s into r to the power minus k, because multiply both sides by r to the power minus k. Then I have r to the power k into s equal to r to the power k into r to the power minus k, which is identity, s into r to the power minus k. Is that clear to all? Okay. Pause, review, proceed. Okay. So now let's go to the next one. Now what did I want to conclude? I don't remember. I think rs into r squared is, yeah. So I have rs into r squared is, right? Is that clear? Yeah. So now r squared is, you know what it is. R squared is, look at that, r to the power k into s is s into r to the power minus k. Therefore r squared is s into r to the power minus k minus 2, right? But remember, r to the power 4 is identity. Therefore r to the power 4, r to the power 2 into r to the power 2 equal to identity. Therefore r to the power minus 2, remember this is the definition of the inverse of r to the power 2. Therefore this is r squared. Yeah. Therefore this is s into r squared. Now use associativity. Therefore r into s squared into r squared, that is r cubed. Yeah. Therefore if I want to fill in the multiplication table, okay, rs into r squared s, this will be r cubed. Okay. Now let us just verify this in a slightly different way. What does rs, what does r squared is? We saw r squared is reflection with respect to y-axis. That means 1, 2, 3, 4 went to with respect to y-axis. Therefore 1, 4, 3, 2, right? Oh, first we have to do r squared is with respect to, right? Okay. Then I have to do rs. What was rs? Rs was reflection with respect to the diagonal 1, 3. That is with respect to this diagonal. Therefore this is r squared is. And now from here I want to go to rs. That means you have to reflect with respect to this. That will go as to, remember it has to 1, 3, that is this. Therefore it will be 1, 4, 1, 2. Reflection with respect to this. Oh, 1, 3, 1, 3. Therefore this will be 2, 3 and 4. You understand? Reflection with respect to this is the line, this diagonal. Okay, that is going to be 1, 3, 2, 4. Okay, let us see whether it's r cubed. R cubed will be 1 goes to 2, 2 goes to 3, 3 goes to 1. Yeah, it went there. You understand this? This is r cubed, because r cubed will 1 will go to 2, 2 will go to 3. Okay, 1 goes here, and one more r it will go here, and one more r it will go here, and 2 is naturally 1 r, 2 r, 3 r it comes here. You understand this? Yeah. Pause, review, proceed. Notice that I am combining the geometry as well as algebra, but this is only to see, because how did I introduce R's, all these things by means of either rotation or by means of various reflections. Okay, the group elements has some geometric meaning for me, but for algebra they don't have to. Okay, he only knows two symbols R and S, that R to the power is identity, S squared is identity, and R S R equal to S. With this he can show what are the 8 elements he is going to consider. He may not know why he has to consider those 8 elements, but he will write them. What are the 8 elements? He will write them as R identity, R, R squared, R cubed, and S, RS, R squared S, R cubed S. These 8 elements. Okay. So what he wants to show, he wants to, with these 8 elements under whatever the operation we have given, okay, they form a group. You follow that? That's what we did. So without looking at the geometry, using only those three facts, r to the power 4 is identity, s squared is identity, r is r equal to s, we can fill in the Cayley table. I did one, and what I did was, by using only that algebra, I got r cubed as the answer, but I wanted to see whether by using geometry also I get the same answer. This is just for confirmation check, because I think mostly in terms of geometry. But if you don't want, but whatever done is good enough. Let us do one more thing. Okay. Okay. So let us do something like RS into RS. Okay. What is RS into RS? Okay. This is very again easy. RS, and RS is, remember, R to the power ks is S into R to the power minus k. Therefore RS is going to be S into the R inverse. Yeah. And what is this? R into S squared into R inverse, therefore its identity. That is very clear, because remember, what is RS? RS is reflection with respect to one of the diagonal, 1, 3, if I remember right. And any reflection, if you carry it out once more, again do RS, again with respect to that, 2 and 4 get interchanged. Right? It is again with respect to this. Don't go by the number now, you should only go by this diagonal. This diagonal, it will go to 1, it will go to 2, 3, 4, therefore identity. Right? And suppose now I have r squared s into r cubed s. Okay. Suppose I want to do that. Then what will I do? I will do r squared s. R cubed s is s into r to the power minus 3, but it is r squared s into, remember, r to the power 4 is 1, that is r into r cubed is 1, therefore r, this is r. Yeah. Oh, yes. Okay. So, but this is r squared. Oh, we don't even need this. This s squared is identity, r to the power minus 3. Therefore, it's r inverse. Okay. R inverse is again r power cube. Let's make sure it's correct. R squared s into r cubed s. R squared s into r cubed s is s into r to the power minus 3, but that is 1, right? So r to the power 1. So I may be making a mistake. Let me just make sure I'm doing it correctly. r squared, okay, r squared s is s into r to the power minus 2. Oh, see, it is r cubed, sorry, r cubed is s to the minus 3, right? So inverse of this is s into r, right? That's correct. Therefore, it's r cubed, okay? So r squared s into r cubed s is this. Let us again go through. What is r squared s? R squared is reflection with respect to y-axis. And what is r cubed s? R cubed s is reflection with respect to 2, 4, line 2, 4, right? So let us do that. So 1, 2, 3, 4 under r squared s, where does it go to? It goes to reflection with respect to y-axis, therefore 4, 1, 3, 2. Now under r cubed s, that is with respect to this axis, therefore 2 and 4 go here. Okay, reflection with respect to this line, right? It is a reflection with respect to 2, 4. 2, 4 is this one, sorry. 2, 4 is this one. Therefore, reflection with respect to that will be, they will remain, 3 and 1 remain, and 2 and 4, the 2, 4, right? This will go 4 and 2. Okay, is that correct? So, R pushes 1 to 2 this place, and once more it pushes, and once more it pushes to this. So it's correct. Therefore, right? And 2 under R it goes to here, 1 R squared it goes here, R cubed it goes here, right? And okay, just make sure you are following. But let us quickly go through that. So R squared s into R cubed s, we have found it. It is going to be R cubed. Okay. One way to do that will be to see. Remember when I filled the Cayley table. Okay. Look at the column. There will be elements of G permuted. They are G1 to Gn. There will be some other fashion. Exactly each element will occur only once. So what I would suggest will be you try to fill only one thing column with respect to this element Rs times. Okay. E times R squared is R squared s. R times this will be R into R squared into S. That is R cubed s. But R cubed s, you know what it is. So you keep on doing like that. Are you following me? Okay. So what I am saying is, let us look at R s. Let us say R squared s. Okay, here E R R squared R cubed s R squared s R cubed s, right? So fill only this column. Okay, this is R squared s. Therefore E into R squared is this. Then R into R squared s, that is R cubed s, and then R squared into R squared s. Okay, that will be R power 4, that is Rs, and S into R squared s, S into R squared s, S into R squared s, that will be S into R to the power R squared, that is this will be R squared. So like that you fill all those things, you will get the idea. Okay, please, I mean, don't give up, just to play with this. Yeah, because simple manipulation of symbols you will learn from high school onwards, so it should be easier, right? So please do that, you will find it easy. The only thing you will notice, the moment I see R power 4, it's identity, S squared, identity, and R as R, I can replace it by S. Okay. Or more generally, R power k S equal to S into R to the power minus k. Yeah, right. Now there are two things which I want to talk about. With that, I'll stop. I think there are still about 14 minutes or so. We'll go ahead. See, therefore, D4, okay, consists of these elements: identity, R, R squared, R cubed, S, RS, R squared S, and R cubed S. Okay, and multiplication, group multiplication, we are already done. Okay, for algebras, what they will say is D4 has only generated by two elements R and S with the relation R power 4 is identity, S squared is identity, and RSR is equal to S, and from this we conclude R to the power Ks is S into the R to the power minus K for every K in M. Okay, with this we can fill the multiplication table, right? Now notice that, so in terms of permutation, you can see I can think of as 1, 2, 3, 4 cyclic permutation, and the permutation, yes, remember it was with respect to the horizontal 1, 2, 3 x-axis, therefore 1 goes to 2, therefore it's 1, 2 and 3, 4, right? You can see R to the power 4 is identity permutation, and S squared is also identity permutation, and then I can see what is RSR, right? So under RSR, where does 1 go? 1 goes to 2, 2 goes to 1, therefore 1. Yeah, see, under R, 1 goes to 2, under S, 2 goes to 1, and again under R, 1 goes to 2. Are you following? So under R is 1 goes to under R, it goes to 2, under S it goes to 1, under R it goes to 2. Next let's look at 2. Under R, 2 goes to 3. Under S, 3 goes to 4. Under R, 4 goes to 1. Right? You see that? Therefore, and now 3. Under R, where does 3 go? 3 goes to 4. Under R. Under S, 4 goes to 3. Under R, 3 goes to 4. And now this is a permutation, therefore 4, where will it go? It will go to 3. Now you can see R as R is this permutation 1, 2, 3, 4. 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Therefore it is 1, 2, 3, 4, which is R, which is yes. Yeah. So D4 is only consists of these elements again. Okay, where R is 1, 2, 3, 4 and S is 1, 2, 3, 4 and all elements R, R squared, R cubed, identity, yes, RS, R squared is R cubed is. Okay, you can see this is another way of concrete way of looking at D4. And there is yet another way. Let us look at 2 by 2 matrices, only these matrices. Look at the matrix R, which is I and minus I, right? Now it's a diagonal element, right? Therefore what is R squared? Minus 1, minus 1. R cubed, it is going to be minus I plus I. And R power 4, again minus I into I, it's a minus I squared, and minus I into I, minus I squared, therefore it's 1, 1. Identity. Therefore R to the power 4 is identity. Next, let's look at S equal to 0, 1, 1, 0. What is S squared? 0, 1, 1, 0, 0, 1, 1, 0. First row by first column 1, first row by second column 0, second row by first column 0, 1. So identity. Then you can check R as R equal to S. Check this. So what do you think I have done? I have shown D4 first completely geometrically. Okay, it arises as possible symmetries of a square. Okay, number one. Therefore, and what did you do? We looked at each such symmetry permutes the vertices 1, 2, 3, 4. Therefore, we thought of this as a permutation. Each is a symmetry. I can write as a permutation. We wrote that. Okay, and is that clear? So, what are the basic symmetries there in terms of geometry? R, which is a rotation by pi by 2 in the anti-clockwise direction, and S, which is a reflection along the x-axis. Then we found out all elements can be written in terms of either R power of the form R power K into S power L. And where does K run from? K run from 0 to 3 or 1 to 4. Where can S run from? It can run from 0 or 1. Do you write? What are the elements? R power 0, R squared, R squared, R cubed. And S, and then RS, R squared is R cubed is. Therefore, you see that all elements are of the form R power K into S power L, where K runs from 1 to 4 or 0 to 3, and L runs only in 0 and 1. Is that all right? So these are the 8 elements. And what is the relation we found? R to the power 4 is identity, S squared is identity, and RSR equal to S. That is algebraic. Then the third thing what we found was I can also write in terms of matrices. R, I can think of it as a matrix, a diagonal matrix I and minus I. S as the anti-diagonal matrix. Okay, and the anti-diagonal is 1, 1, 1. And the diagonal way 0, 0. Then also we can check. So it is like the same character comes in different disguises, right? The group D4, the dihedral group, arose as the group of symmetry of a square, which is Cavali's geometric way of thinking. The second thing is purely algebraic way of thinking. That is, it has only two elements, basic elements R and S, and all other elements of the D4 can be written in terms of R and S. And to do, and also we can do the binary operation, group operation. Okay, right? What is that? The group operation, we know what it is, right? By using RSR equal to S. You see R power Ks equal to S into R power minus K. We did that. The third is in terms of matrices. So you can see they are different avatars, but not even avatars, they are actually disguise. Okay, are you following? It is I know for a BSc student it will be highly overwhelming. That is why teachers don't teach, but I believe you are capable of understanding. The only thing you need is to discuss it with your friends. Go through it once or twice. Okay, since the timing is short, I don't want to talk about dn for n greater than or equal to 3. Okay, if necessary, I will follow it up in the next session or a separate session altogether. But D4 is already good enough. Okay, you can forget everything, forget the geometry. You can only focus on the algebra. R, yes, R power 4 is identity, S squared is identity, R as R equal to S, R to the power K is equal to S into R to the power minus K. With this, I can do everything. Algebras usually do only this. And there are two concrete way of looking at. One is by in terms of permutation. We did that. R equal to cycle 1, 2, 3, 4. S equal to product of two transpositions 1, 2 and 3 or 4. Okay. And we can also look at the dihedral group as a matrix. What is that? R, take it diagonal I and minus I. Diagonal matrix 2 by 2 matrix. And S equal to the anti-diagonal matrix 0 1 1 0. That is anti-diagonal will be 1 1 and diagonal will be 0 0. Right? Please go through, discuss. As we go along, we'll make use of this group, this example at many places in the future also. Okay? And don't give up, discuss with your friends. Okay? And also you may download my article, but unfortunately my article deals with the general N. Okay? So the best will be to go through this video twice with friends. Have a pen and paper, do on your own. I forgot in the first 10-15 minutes PRP. I'm sorry for that, but you know when to stop. Okay? The moment I wrote down the symmetry, first make sure you understand, and the reflection symmetry, make sure you understand. Then all the 8 symmetries I wrote, go back, understand, PRP at those places. Okay? At each level, I also wrote down the permutations, also go through them. Okay? I hope you enjoyed. Of course, it's a tough, but I'm sure you will begin to like it. We will meet again. Thank you. Bye.